Hi there. All right, here we go again. Today's another amazing lecture by your Chem Coach Powers. Um, right? It's amazing. Here I am, all distorted and crazy. Seriously though, excited about today. Today we're going to talk about the quantum model of the atom. Okay, so we're developing from the Bohr model to the quantum model and what this now looks like. This stuff is so cool. Like, remember I told you it was more complex, way more complex, and the math on this stuff is just amazing. Anyway, so let's look at what we've got here. And what we're talking about today, quantum model of the atom. Our objectives, let's look at that modern model of the atom, or the quantum model of the atom. You should be able to describe it to me. So when you walk out of here, you're going to tell me about the main feature, orbitals, not orbits, but orbitals. They're different, okay? And you're going to tell me about size, shape, and orientation of each of those orbitals. And then I want you to just kind of get a visualized picture, right, of the representation of the quantum model, and then be able to tell me why it's different from Bohr's model, okay? And there's lots of things that are different. Okay, so just as scientists had started to look at the idea that light was now a particle, there were other scientists like Louis de Broglie who was looking at electrons and thinking, you know what, I think those are actually like waves. And since electrons are vibrating, they vibrate at different frequencies, that's going to be a lot like a wave. Okay, so kind of coming across some pretty cool idea. We knew that electrons were particles. Now we're starting to get some evidence that they are also acting like waves. Well, that's going to change our model of the atom entirely. If they're not just particles, now we can understand their vibrations, we can understand their frequencies. And so what we started figuring out, several different scientists, for instance, we've got Heisenberg uncertainty principle. You guys have probably heard of Heisenberg before. It's impossible to determine the exact location of the electron and know where it is in space at a particular time. Okay, the probable location of the electron is described using 4 different quantum numbers. These are basically like the address for electrons. Okay, so we're going to now have this term called orbitals, which is going to describe the electron cloud. Basically, it's a 3D location in space where the electron is likely to be found. How likely? About a 90% probability. Again, these electrons can zip out and be in different places than their orbitals, okay? But the orbital is the location 90% of the time where they're likely to be found. Orbitals can only hold 2 electrons at max. They can hold 1 or 2. That's all that can be held by any particular orbital. Okay, so let's look at it. First of all, we have the principal quantum number. Now, that principal quantum number or energy level corresponds to the 7 different periods on your periodic table. Okay, 7 periods on the periodic table, 7 different energy levels, 7 different quantum numbers. These are the principal energy levels of principal quantum numbers, 1 through 7. The higher the principal quantum number, the more energy is going to be in that principal quantum level. Then we have the angular momentum quantum number, which is the L, okay? And this is basically the shape of the orbital. We can have spherical orbitals, dumbbell-shaped orbitals, and they can get more and more complex. But we basically have S for spherical, P has dumbbell shapes, D is more complex, and F is even more complex. And we give them these different numbers. It's not really important that you understand what these different numbers are right now. You're not going to have to use these on a test. Maybe in college you will. But for right now, just know that the second energy, or the second quantum number, talks about the shape of the orbitals. Then the orientation is our magnetic quantum number, or M, and the orientation is going to have a few different indicators as well. Some of them have lots of indicators, up to 7 different indicators as to the orientation. And then the spin is going to be either a plus or a minus half. Basically, the electrons are either spinning in one direction or they're spinning in the other direction. And we don't necessarily even know which direction they're spinning, but we do know that if they're in the same orbital, that they must be spinning in opposite directions, okay? Now, this is actually kind of cool because if you've ever wondered what is magnetism affected by, it's actually affected by how many electrons are spinning in a particular direction inside the atom. So it's pretty cool. All right, so remember, our energy level has to do with the average distance that we are from our nucleus, and then we have 7 different energy levels that we can have, right? It also can tell us the number of orbitals. So N is the principal quantum number. So if we say our first energy level, 1 squared, that means that we can have one orbital, okay? The number of electrons is 2 times 1 squared, so we can have 2 electrons. Let's say we're in our 7th energy level, all right? 7 squared, 49. We could have 49 different orbitals, okay? And then the number of electrons, 49 times 2, right? So we never are going to have that many electrons in that 7th energy level. That 7th energy level at this point only has a maximum of 8 electrons, okay? Because this is the quantity that it could hold. It's not the actual amount that it does hold, okay? These numbers that we're figuring here. But if you calculate this for the 4th energy level, 4 squared, 16 different orbitals, yes, that happens. And 2 times 4 squared, 32 electrons. Yes, you can get 32 electrons in the 4th energy level, okay? You can do that to the 4th one. If you go to the 5th energy level, again, we haven't discovered elements that actually have that many electrons yet. So no, that is not true up to the 5th one yet. Maybe someday when we discover higher elements. All right, 2 electrons per orbital, don't forget that. How many electrons can be found at the 3rd energy level? How many electrons can be found at the 3rd energy level? 2 times 3 squared. 2 times 9 is, good job, 18. All right, here we go. Now, sublevels. This is our L, our 2nd quantum number, right? Tells us the shape. Now, what are our shapes? Well, our shapes for the 1st energy level is a sphere, 2nd energy level is a dumbbell. Let's talk about those two. At the 2nd energy level, n equals 2, there's 2 sublevels available to be filled with electrons. You can fill up the S sublevel, S, or the P sublevel, okay? So the S sublevel or the P sublevel can be filled with electrons. Further away from the nucleus you go, the more space there is for more types of orbitals. We have 4 different types of shapes, and here they are. Here's the spherical, okay? And again, it's designated L is equal to 0. Don't worry about the numbers right now. All right, each energy level contains 1 s orbital. You notice how they're getting bigger in size, the bigger average distance, right? So 1s, 2s, 3s. And these things would be stacked on each other. As you get more and more elements, or atoms, more and more protons and electrons in an atom, you're going to stack these things one on top of the other. It's kind of like the Russian nesting dolls, right? They're just going one on top of the other. And the orientation is just one orientation, okay? That's that 3rd quantum number is M. Only one orientation. They only are in one direction. Now, our p orbitals now can be dumbbell shaped, and they have 3 different orientations, all right? So you have 3 different orientations. Remember, you can have 2 electrons here, you could have 2 electrons here, and you can have 2 electrons here. If you have enough electrons, you can have 3 p orbitals, each with 2 electrons, and this is only taking place once you get to the 2nd energy level. Okay? Woo! Now let's look at D. The shapes are getting more interesting, aren't they? We have 5 different orientations, 5 different ways that these things can exist, and you'll notice that some of the shapes are crazy. I want you to know that there are mathematical formulas that describe the shapes of each of these. And again, remember we talked about Bohr's model and how the math just didn't apply once you got past hydrogen? Well, as you get to these, you can see why the math might get a little bit more complex, okay? Again, 5 different orientations that you have here, 5 different sublevels. Here are the different F sublevels. Now, again, I want you to pay attention. Although this is kind of like crazy, you got stuff all over the place, there are 2 electrons that could be anywhere in these little spaces. 90% probability that those 2 electrons are going to be found in one of these little places that are jutting out, okay? And so this is the F sublevel. You can see how complex this must be getting if you just keep doing it. Now, let's look at what they stack like, okay? So if I have my 1s would be somewhere inside, and my 2s is going to be my red. That's going to be the sphere. Notice how these are all a whole bunch of different dots. This is the cloud model, basically showing that all these little dots are a place. Like if you were to take a bunch of pictures of the electron in various different times, this is where they would be 90% of the time. And then once in a while, you might have the electron go like, hey man, I'm over here now. Okay, now I'm here. Every once in a while. But 90% of the time, they're going to be in this vicinity. So we have that red. Boom, that's inside there. And then we have our 2p. That's that first dumbbell. And then we have another orientation of 2b. That's that other dumbbell. Okay, so all stacked together, they look like this. And again, how many electrons do you have there? You can have 6 electrons in there. 2, 2, 2. Now again, you could have 2 electrons on this side, and then they could both come over here. You could have 1 on each side. It doesn't mean that you've got 1 on each side all the time. The electrons are just zipping around all sorts of random places. and they can be in the same side of the orbital, but they can not have the same spin. They must be spinning in opposite directions. Okay, so, and here we go. So what does it look like if we put them all together? Now you can see the 1s is inside there even more. So there's a 1s way inside there, smaller, a 2s that's bigger, and then you've got the 2 p's all there as well, and now you've got the 3 s's, the bigger circle around out here. So this is a model of magnesium. It's got 12 electrons, and it's got 1, 2, 3, 4, 5, 6 orbitals, okay? Holding 12 total electrons, 2 electrons in each one. This is what it would look like stacked on top. You can imagine it could get pretty complex. Here's radium, all right? And of course, it's a slightly different model, but oh my, right? That would be kind of crazy and wild and fun. So let's summarize this. What would this look like? I want you to take a second, pause, and come back and, kind of create this table. Tell me if you can fill this table out and show me what these things look like, okay? All right, you ready? And you're back. All right, good deal. All right, so the number of, well, first of all, our shape. Remember, this is a sphere, okay? Sphere shape. Number of orbitals. We only have 1 orbital, the s. Number of electrons. We've got 2 electrons. My shape, we like to call these dumbbell, okay? Dumbbell shapes. My number of orbitals, I can have 3 orbitals in the p sublevel. My number of electrons, I could have a total of 6 electrons, 2 in each of the 3, right? My shape for my D, I like to call these cloverleaf. I don't know. It's got 5 different orientations, right? Our orientation, we've got 5 different orientations. Remember, this one had 3 different orientations. And so how many orbitals can we have in the D? Well, we can have 5 different orbitals in 5 different orientations. My number of electrons that I can hold in D is going to be 10, okay? 5 times 2, right? And so shape of F, I don't know what the names of these are. I can just call them crazy. The number of orbitals, we can have 7 different orbitals here. And then the number of electrons, we can have 14 electrons. You're like, Powers, cloverleaf, and crazy, is that really okay? You know what? I've never had to know the names of those, so you're probably not likely to have to know the names of those because I'm sure they've got different names. I've never even looked them up. I wouldn't worry about it, okay? Don't worry about it. You just got to get the basic concept, right? If you can fill this out, don't worry about the names of those 2. Not such a big deal. This is pretty common. That's the way we call that. I don't know. Another country, they might call it something different. So it's not like the names matter that much. But you should know sphere, and you should know dumbbell, okay? All right. So can we now do this? Okay, so there's a little pause. Explain how the quantum model of an atom is different from Bohr's model of the atom. All right, pause it and practice. Boom, you're back. Okay, so the quantum model has got a lot of differences, right? We have these shapes of orbitals and not orbits. Okay, we still have energy levels, and so that's important, right? The Bohr, that's a similarity. But now we have all of these different orientations. We have spins that we're talking about now. We didn't talk about that. We have certain locations and spaces. So lots of little differences between Bohr's model. Okay, can we now describe the modern model of the atom? Yeah. We now know how to do a quantum address, at least generally. In college, you were very likely to have to actually write out the quantum address. I wouldn't worry about that right now. The quantum address would just be, something like 0, 1, -2. How about 0, 2, -2, 1/2, or something like that. That would be a quantum address, and it would tell you which element on the periodic table you're actually, dealing with. Not important for right now. You're not going to have to know that for our test. You can describe the main features of the quantum model. Yeah, orbitals. Boom. Now you know different shapes where the 90% probability of finding an electron. And of course, we now know different orientations and shapes and sizes. You can visualize and represent the quantum model and explain how it's different from the Bohr model. Yeah. You good. You amazing. You smarter now than you were before. And that's exactly what we're here for. I hope you had a good time learning about the quantum model of the atom and how we are figuring out more and more cool stuff about stuff that we can't even see. Wow, isn't that wild? All right, have an awesome day. Be kind to one another. God bless you.